Okay, today we'll talk about waves. Okay. Now, if you guys remember last chapter, we talked about a harmonic oscillator. So a mass attached to a spring. Okay. If you stretch this mass from its equilibrium position and let go, it would oscillate. And that was that was a simple harmonic oscillator. In a wave, you have a whole bunch of harmonic oscillators, okay, oscillating in coordination. Okay, so this is a simple harmonic oscillator. And now let me show you a wave on a string. Okay. So here's a wave, and we want to observe some features about it. Each point on this, each element on the string is executing simple harmonic motion, just like that mass attached to the spring. Okay. Now let's notice a few features about this. See, as the wave is traveling, you see the medium is not traveling. This green string is not going anywhere. It's oscillating in place. Okay. But the disturbance is traveling. Okay. So when a wave travels in a medium, it's a disturbance that travels. Okay. The medium itself is not transported. All right. How's the wave being set up? This guy is pumping energy into the medium. Soon as this guy stops, soon as you stop pumping energy into the medium, the wave will stop. Well, the energy that was pumped, that will travel away, but no new energy will be pumped, and that wave will stop. No new wave will be set up. All waves carry energy. How do we know that it carries energy? Can you think of some way of demonstrating that? I'm sorry? I'm sorry? Say it louder. Yeah, so you know that electromagnetic waves get to you, and energy gets to you. Here's another way to demonstrate it. So let's say this is a water wave, and if you anchor a boat there, the boat will bob up and down. It takes energy to lift the boat up and down. Okay, so all right, so all waves carry energy. Okay, so let me summarize this again. A source is pumping energy into the medium, which is being carried away. When a wave travels in a medium, the medium itself is not transported. Okay, it's the disturbance that travels. Waves carry energy. Okay, and when you have a wave in a medium, it's a bunch of harmonic oscillators oscillating. Okay, so we'll study all these properties. Okay. We'll also be interested in the following. We'll introduce to you a new differential equation. Okay, so here is a dynamic system. Here's a system that is evolving with time. We want to mathematically model its behavior. Okay, and that mathematical model, an equation that describes its behavior, it'll be a differential equation. Okay, so let's say that dotted line is the undisturbed position of the string, and y is the displacement of the string. Okay, and you see that displacement is changing with x, and it's also changing with time. Okay, so I'll give you the differential equation right now, and then we'll come to it later. Okay, so what we want to do is give you a differential equation that describes the behavior of the system. And here's the differential equation. All right, so here's the undisturbed position of the string, and here's a snapshot. There's y. It's a function of x and t. This is x, this is x, y is a function of x, and as time goes on, this will change as well, okay? And it turns out that, so this is the second differential equation you'll see. Del square y x t by del x square equal to 1 over v square del square y. And this is the wave equation. Okay, so let me remind you of the other differential equation that you've seen. Okay. So here was a system. You had a mass attached to a string, and you set it in oscillation. This would oscillate like that. And the behavior of that system was given by this differential equation. D square x Okay, now let me mention a couple of things about this. Okay, this is the derivative is with respect to one variable. Have you guys done partial derivatives yet? No. Okay, well, we'll do that in 2 seconds. Okay. Look at this equation. Here's a function of, it's a multivariable function. This is relating the derivative of this function with respect to x, the spatial derivative. It's relating it to the time derivative of that function. Okay, here's a partial differential equation. Okay, so this is the wave equation. Again, what are we trying to do? We are studying a system, and its evolution, the system's evolution is governed by this differential equation. And then we go find solutions to these differential equations, and we know the behavior, the various, all possible behaviors of this system. And that's the idea. Okay? All right, so now I'm going to give you a very brief introduction to partial differential equations, and then we'll get into the slides. Okay? How many of you know partial differential equations? And you've done partial? Are you in Calc 3? Okay. All right, so let's do partial differential equations briefly. So let's do the following. Okay, so so let's say z is a function of x and y. Okay. And we'll do an example. Z x y is x squared y cubed. I'm just using a simple example. Okay. Now you can ask the following question. Let's say, so I'm on this surface, and how does z change when I travel parallel to the x-axis? You guys understand? For 1 unit distance travel along parallel to the x-axis, how does z change? And that is given by this partial derivative. Del z by del x tells you how z is changing as you're traveling parallel to the x-axis. Okay? So this is taking change in z when you travel parallel to the x-axis. And how do you take this derivative? Well, you treat the other variable as if it's a constant. Del z by del x is 2xy cubed. And this is telling you how z is changing as you travel parallel to the x-axis. Okay. you can calculate it at any location. So if you put x, y values, you're calculating at that particular location how z is changing when you travel parallel to the x-axis. Okay, so that's what the partial derivative means. What does del z by del y mean? Well, let's first calculate this. What is del z by del y?
3y squared.
Yep, it's x squared, 3y squared. Okay, so you're treating the other variable as constant. And what does this mean? Well, at this location, at any given location, how is z changing when you're traveling parallel to the y-axis? This guy means how is z changing when you're traveling parallel to the x-axis? Okay. All right, so going back to so now that you know partial derivatives, now you can understand this. So this is relating the second order partial derivative with respect to x to second order partial derivative with respect to t. Okay, and this is called the wave equation. Okay, so this is the second big differential equation that you've studied. And what does this differential equation do? It's describing the evolution of this guy. Okay? The behavior of this guy, this string, okay, no matter what you do, where you hit it, the behavior of this guy obeys this differential equation. Okay? So you can take a guitar string and make it vibrate any way you want it, it'll obey this differential equation. Okay? And all possible ways in which a guitar string can vibrate will be solutions to this differential equation. Okay? That's the idea. All right, so now let's get into the slides. Okay, so we'll talk about transverse and longitudinal waves. We'll define these parameters for the wavelength, frequency, and speed of waves. Yep. Energy and power in the waves and wave equation. And we'll talk about superposition and interference. Okay. You know, let's say multiple people are talking and what is the signal getting to a person. Okay, so that'll be superposition of waves. And we'll sometimes the waves will add, they might cancel, and so on. We'll talk about standing waves. What you generate in all musical instruments is standing waves. Okay, and then resonance. We've already talked about resonance. Okay, there are different types of waves. Mechanical waves are waves that need a physical medium to travel in. Okay, sound waves are mechanical waves. These sound waves are traveling in the air in this medium. That they can travel through solids as well, and so on. Sound waves cannot travel in vacuum. Okay. So you saw that this guy is a mechanical wave. Here's a wave traveling on a string. That's a mechanical wave. Waves traveling on the water surface, those are mechanical waves. Okay. And then there are electromagnetic waves that can travel through vacuum. So here's an electromagnetic wave that can travel through vacuum. So for instance, sunlight gets to you through 100 million miles of perfect vacuum, almost perfect vacuum. It's called an electromagnetic wave because it contains both electric and magnetic fields in it. Okay. All right, see, this is the electric field. The electric field is oscillating like that, and the magnetic field is oscillating in a perpendicular direction, and that's the direction of travel. Okay, so if you use your right hand, okay, if you use your right hand, your thumb, this is the direction of the electric field oscillating, this is the direction of the magnetic field, and that's the direction of travel. Okay, so at this spot, right now the electric field is pointing like that. Half a cycle later, it'll be like that, okay, and so on. So that's the direction of propagation. The electric field, magnetic field, and direction of travel form a right-handed coordinate system. All right. So Here's a wave that does not need a medium to travel in. This wave will travel in vacuum. Okay? So there are mechanical waves, electromagnetic waves, and matter waves. And we'll talk about these guys later. I'll show you this video, but I don't want to interrupt the lecture now, so we'll see this at the end. Okay. All right, so most of what we'll talk about will apply to both mechanical and electromagnetic waves. Okay. You saw that all waves carry energy. When a wave travels through a medium, matter is not transported, only the disturbance travels. Okay? So for instance, when this wave travels through the water, only the disturbance travels. The lake is not going anywhere. You can have waves traveling on a lake. Okay, the water is not flowing anywhere. Okay. Transverse waves. So you saw that in the string. Okay. So this wave is traveling in that direction. The wave is traveling like that. But each particle of the medium is oscillating perpendicular to the medium. Okay. That is a transverse wave. Okay. When the particles are oscillating perpendicular to the direction of wave travel, that's a transverse wave. Okay. A longitudinal wave is when the particles are oscillating parallel to the direction of travel. And a sound wave is like that. So let me show you that example. Okay, so here's how you can create a sound wave. So this is air. All you need is a diaphragm that oscillates. And this is pumping energy into the medium. As this is oscillating, you can see there's a red dot there. One of the air molecules is highlighted. And that is oscillating parallel to the direction of travel. And that is a longitudinal wave. Okay? So in a longitudinal wave, particles oscillate parallel to the direction of travel. In a transverse wave, particles are oscillating perpendicular to the direction of travel. A water wave is a complex wave. In a water wave, as the wave is traveling to the right, the molecules on the surface are going in a circular pattern. Okay? And you saw that a circle is a combination of this oscillation and that oscillation. So water wave is a combination of a transverse and a longitudinal wave. Okay? So it's a complex wave. Now, in a water wave, as you go deeper, the size of the circle gets smaller and smaller. Okay? And eventually, you can get to a depth, large enough depth where those molecules are not oscillating. It's only at the surface that you have the maximum amplitude oscillations. All right, so in a transverse wave, particles oscillate perpendicular to the direction of travel. In a longitudinal wave, particles oscillate parallel to the direction of travel. Okay? Water waves are complex waves, so the molecules on the surface travel in circles, and they're a combination of transverse and longitudinal waves. Okay, this is the amplitude. The amplitude is so this is the equilibrium position of the string. The amplitude is the maximum displacement from the equilibrium. And the amplitude is related to the intensity of the wave. So the louder the sound, the greater the amplitude. The higher the intensity of a laser beam, the greater the amplitude of the electric field. Okay, so the amplitude is related to the intensity. This is the wavelength. Okay, okay, so the wavelength there. This is wavelength, that's wavelength, that is wavelength. So crest to crest distance is the wavelength. In light, the color of the light is related to the wavelength. So red light has wavelength of about 650 nanometers. Blue light has wavelength about 400 nanometers. and so on. So the wavelength is related to that. Um, the period is the time it takes for one oscillation, okay? Or it's the time it takes if you're standing there for one wavelength to pass you. If you're standing there, the time for one wavelength to pass you is the period, or also the time for one oscillation. Okay? Frequency is if you're standing there, how many waves will pass you per unit time. That's the frequency. Okay? It also is how many times at a given point will oscillate per second. So you can think of frequency in two different ways: how many waves will pass you in 1 second, or how many times that particle will oscillate per second. Frequency is inversely related to the period. Okay? So 1 over the period is the frequency. Okay, when we do the mathematical description, so again, we learned that what we want to do is we want to mathematically model the behavior of the system. We want to find out the equation that governs the behavior of the system, which I already gave you. I didn't derive it. I gave you the wave equation. Okay, and then we'll learn to solve that equation. So when we write the solutions to that wave equation, these parameters will be convenient. We'll write the solution in terms of these parameters. The wave number denoted by k is 2 pi divided by lambda, and it's called wave number because in 2 pi how many waves are there. Okay, so that's the wave number is that parameter. The angular frequency is 2 pi times f, the linear frequency. Okay, so that gives you the frequency in terms of radians. You can think of it that way. So the angular frequency is 2 pi times f, which is 2 pi divided by that. So these two parameters will be useful when we write the solutions to the wave equation. Okay. All right, now let's understand the following. Okay, so this is important for the next few slides. Okay, so let's do a little example. So we'll learn a neat little trick. All right, so let's say you have this function. Okay, so here's this function. Now what I want to do is I want to shift this function to the right, let's say by 5 meters. How do I shift this function? How do I make it move to the right? By distance d. Do you guys remember from your calculus classes? So if you want to shift it to the right, x minus d. That's how you shift that function to the right. What if you wanted to shift it to the left? I'm sorry? So if you wanted to shift it to the left, fx plus a. Okay? So now you learned how to shift that function. Okay, now let's do a slightly more complicated thing. So here's the function fx. All right, you learned how to shift it to the right. Now I'm going to ask you this. Now I want, instead of shifting it to the right by 5 meters, now I want it to move at the speed of 5 meters per second. I want a moving pulse. How do I do that? You guys understand the question? So this was a static shift. Now instead of a static shift, I want it moving at a certain velocity. I'm sorry? Okay, so if I put a scalar in front of that, it just makes it bigger or smaller. All right, so let's say, so I'll work you along with it. So if I want to move it at 10 meters per second, after 1 second, how far is it? 10 meters. After 2 seconds, 20 meters. Okay. So if I want it to move at a velocity v, all I have to do is replace x by vt. Did you guys understand that? Okay. So this would be the distance v times t. Okay. So that's a pulse moving to the right at velocity v. What is a pulse moving to the left at velocity v? X plus vt. Okay. All right, so now you learned a very important lesson. You learned how to get a pulse moving to the right or moving to the left at any velocities. Okay? So we use this simple example. It could be any function. Okay, so let's do the following. Okay. What I've drawn is sine x. Okay. I've drawn that function. Okay, now what I want to do is I want to move this guy at velocity v. Okay. So so there is the snapshot of it at a later time. How do I write that? Fxt would be a sine x minus vt. Okay. So there is a sine wave moving to the right at velocity v. Okay. Now, so this was a sine wave. This was a sine x, just a sine x. Now, if you have a certain wavelength, if this is the wavelength, then this function yx is a sine 2 pi by lambda x. Okay, let's make sure we understand this. At x equal to 0, this is 0, sine, and y is sine 0. At x equal to, what is this value of x? This is lambda, so this is lambda by 2, this is lambda by 4. This is x equal to lambda by 4. Okay, so if you write x equal to lambda by 4, the lambda will cancel, then you get sine pi by 2, which is 1. Okay, so let's make sure a sine 2 pi lambda times lambda by 4, the lambda cancels, 2 sine of pi by 2 is 1, and a is the amplitude. Okay, so this works out. And for x equal to lambda by 2, lambda cancels, sine of pi is 0, and you have 0 there. Okay? So here's how you write a sinusoidal function whose wavelength is lambda. And now you know how to move this guy to the right. So y x of t would be a sine 2 pi by lambda x minus vt. All right, so we've learned an important thing. As a wave whose wavelength is lambda, now you've learned how to move it to the right at velocity v, okay, which is this guy. So now you have learned how to write a traveling wave of any wavelength. Okay? To the right, it was x minus vt, and if you wanted to move it to the left, what would it be? X plus vt. Okay? So you've learned how to mathematically describe a complicated thing. Okay? All right. So now let's get back to the slides. Okay. So you learned how to make a pulse travel to the right. All you do is replace x by x minus vt. You want it traveling to the left. It would be x plus vt. All right, so you saw that, okay. We'll have to come back to the, okay, so you saw that a pulse traveling to the right would be a sine 2 pi by lambda x minus vt, okay. Now you'll see in a second that v, the velocity of the wave, is given in terms of the frequency and wavelength like that, and that is equal to omega by k. Okay, omega is the angular frequency. That's why we introduced those two parameters. Omega is 2 pi f, and k, the wave number, is 2 pi by lambda. So the 2 pi cancels. It's equal to f times lambda. Okay. So this is a sine k x minus omega by k t. That would be kx, the k would cancel, and that would be omega t. So a sine kx minus omega t. Okay, so a sine wave traveling to the right is given by a sine kx minus omega t. K is the wave number, omega is the angular frequency. A sine wave traveling to the left would be kx plus omega t. Okay? All right, so you now know how to write a sine wave that's either traveling to the right or to the left. Okay? Plus is traveling to the left, minus is traveling to the right. K is related to the wavelength, omega is related to the frequency. Okay? All right, so now you learned that. All right, so what is the speed of the wave? So here's this wave at a given instant. A little later, it's to the right. You want to know how fast it's traveling. Okay? So you want to know the speed at which this point is traveling. Okay? So it turns out that as this is traveling to the right, this argument is called the phase, and as time increases, that point travels to the right, keeping this constant. The phase is constant, so kx minus omega t is constant. And then you take the time derivative of that, dx by dt, that gives you the speed of that point, dx by dt, which is the velocity of the wave, and that works out to, so this is 0, and dx by dt works out to omega by k, which is equal to that. And that is the wave velocity. So that's the speed of the wave. So you want to remember this formula. Speed of any wave is frequency times wavelength, and it's equal to angular frequency divided by the wave number. Okay? That's the speed at which the wave is traveling. All right, so there's the what is this? This is a sine wave traveling to the left, which has a wavelength given by that guy and whose frequency is related to that fellow. Okay. So now you've learned how to describe sine waves that either travel to the right or to the left. Okay. And it's given by this equation. Okay. So this is a so y equal to a is the amplitude of the wave. The amplitude is this fella. And what is the amplitude related to? It's related to the intensity of the wave. Now, when I talk louder, what did I do? I increased the amplitude of my wave, okay? Sine kx plus, that's a wave traveling to the left, minus is wave traveling to the right, omega t. Okay? So you've learned how to describe a traveling sinusoidal wave. Okay. All right, now let's go back to that simulation. All right, I'm going to do the following. All right, so let's go back to normal speed. Okay, so there's the normal speed of the wave. Okay. Now imagine a string, a steel string, and a cooked noodle. We'll connect those two to this oscillator that is pumping energy in. So a steel string under tension and a cooked noodle. I mean, there's only so much tension you can put on a cooked noodle. On which would the wave travel faster? The noodle? Okay, so we are going to decrease the tension. And you can see that the speed at which the wave travels decreases. Okay, so greater the tension, greater the speed of the wave. Okay, and this wave speed will also depend on the weight of the string. Okay, so the speed of a wave on a string depends on the tension in the string and the mass per unit length, which is mu. So those are the two parameters on which the speed of the wave depends. Okay. All right, so you saw that each element of the string, okay, is oscillating in simple harmonic motion. Okay, and as the wave travels to the right, energy is traveling to the right. Okay, so each element is oscillating in a simple harmonic motion. Okay, the rate at which energy is transmitted. So you can stand here and ask how much energy is passing you per second. Okay, so going to this guy, you can stand there. Okay, you're standing there and you can ask how much energy is passing you per second. Okay, so and this gives you the power. It tells you how much energy is passing you per second, and that is 1/2 mu. Mu is the mass per unit length of the string. V is the velocity of the wave. Omega is the frequency. And A is the amplitude. You see, so the power is dependent on amplitude square and frequency square. Okay. So these two parameters, the mass per unit length of and the speed of the wave, depend on the properties of the string. So these guys depend on the properties of the string, while the frequency and amplitude depend on the wave generator. Okay, so The last two parameters, the frequency and amplitude, depend on this guy, and mass per unit length and velocity depend on the properties of this guy. The velocity depends on the tension in the string. Okay, so there are two parameters that depend on this guy and two parameters that depend on that guy. Okay, so the more energy you put in, the faster energy the greater the rate at which energy will travel away. So power is given by 1/2 mu v times omega squared times amplitude squared. So the dependence of the average power on square of the amplitude and frequency is a general result, and it's true for all types of waves. Okay, so for electromagnetic waves, a more intense laser beam will have a greater amplitude of electric fields and magnetic fields. Okay, so so a more intense laser beam, the amplitude of the electric field will be greater. You increase the amplitude by a factor of 2, the intensity of the laser beam will increase by a factor of 2 squared, 4 by a factor of 4. Okay. All right, so here is the wave equation. Okay. And again, we're not deriving it, we're just giving it to you. Okay. So this is a new type of differential equation. The behavior of that string is governed by this differential equation. Okay. You see, this is a partial differential equation. It's relating, the neat thing about this is, it's relating a spatial derivative, how this y is changing with x, and it's relating that to how that y will change with respect to time. Okay, so you're taking derivatives with two different variables and they're related to each other. Okay, the general form of this equation, the general form of the solution is like that. Okay, x and t appear in that combination. Okay, in all solutions. So you can take a guitar string and make it vibrate any way you want, and the solution will have that form. Okay. All right, and we showed you one of the solution was y. So here's a simple solution to this equation, kx minus omega t, okay, where v in that equation is related like so. Okay, I'm going to show you just for 1 second, we'll take a second and show you that this is indeed a solution to that equation. Okay, we said that the string that is vibrating, this fella is a solution to that wave equation. Okay, so let's show you that. Okay. And again, we gave you the wave equation. So here was the wave equation, del square y x t del x square was equal to 1 over v square del square y x t del t square. And here was the wave equation, and we are telling you that here is a solution to this wave equation. Okay, so let me show you that this is indeed a solution to that wave equation. Okay, so help me out with these derivative. What is del y by del x? What is the partial derivative of this guy with respect to x? Derivative of sine is cosine. A cosine kx minus omega t, and then you would get a k out of there. So you take the derivative of that, and then the chain rule derivative of this with respect to x, that'll give you a k. So you have a k. Now I'm going to take this derivative a second time. So I'm going to take the derivative of this function with respect to x. Derivative of cosine is negative sign, very good. Okay. And then I get a k again. So minus k squared a sine kx minus omega t. Okay, we got that. All right, now let's do the time derivative. There you go. All right, you guys are all experts now, so I'll do it fast. Again, derivative of sine is cosine, a cosine kx minus omega t, and then you get a minus omega, so minus omega. Okay, del square y by del t square, derivative of cosine is sine, negative sine, so, and then you get negative and negative omega square a sine. Okay, so you get minus omega square a sine kx minus omega t. Okay. Okay, what was our wave equation? Del y square del x square should equal 1 over v square del square y by del t square. Okay. Del square y by del x square was this term. So minus k a square sine kx minus omega t. Is that equal to 1 over v square? Del square y by del t square was this fellow. So let's put that in there. All right, this guy cancels. That's a good thing. The minus signs agree. Okay, so now the question is k a square equal to 1 over v square omega square a square? Okay, again, a square cancels, good thing. Is v square equal to omega square by k square? Yes, it is indeed. Okay. So what we have shown you is the following. We weren't deriving anything, but we showed you that this is a solution to that differential equation, that wave equation. Okay, so this is one way in which that string can vibrate. So that's a pure note on a guitar string. Okay. And of course, there are other ways it can vibrate. All right. Now that we've studied a wave traveling on a string, what we'll do is we'll do more complicated things. We'll send multiple waves down a string. Okay. So we'll have a string, we'll hold a string, and we'll do the following. Okay. We'll send a pulse down from the left end, and we'll send a pulse down on that string from the right end. Okay, and we'll see what happens. Okay, so let me show you what happens. Okay, so here we go. So you see, we send a pulse from the left and one pulse from the right on the same string. what do you guys see? When they're at the same location, they interact, and then they'll pass each other. And after they've interacted, have they changed each other's nature? No, they're exactly the same. Okay, so when they're at the same location, they will interfere, and all they're doing is just adding up. So if the pulses are the same sign, then you get a larger amplitude. And if the pulses are of opposite sign, you get a pulse of a smaller amplitude. Okay. So if two pulses travel and they meet at a location, they'll interact, but they do not change each other's nature, and then they'll keep going. Okay. All right, so that is interference. Okay, so all right, so we have two pulses here, and when they get to the same location, you see the resultant pulse is bigger. When they have the same sign, the resultant pulse is bigger than either one of them. This is called constructive interference. And then after they interact, they'll move away, and they have not changed their shape. Okay, so interference is the phenomenon of waves in the same region of space combining to produce a resultant wave. So that's interference. Okay. Constructive interference is when you get a larger resultant amplitude. Destructive interference is when you have waves of opposite signs. Okay, so if this amplitude was exactly equal to that, then they would exactly cancel each other. Okay, but if the resultant pulse is smaller than either one of them, then you have destructive interference happening. Okay. All right, so now what we'll do is, you saw a sine wave that was traveling. Okay, what we'll do is we'll have two identical sine waves travel in the medium in the same direction. You can do this using a speaker. You can use two speakers, set the speakers on the left side of the room, and you can have those play pure tones and travel in this air. Okay, so let's say you have two pure tones traveling to the right. Here's the mathematical equation. Okay, so there is one wave traveling to the right, and here's another wave. You see they have the same wavelength and same frequency. K and omega are the same. Okay, and this is a phase shift. Okay, if this fellow is 0, then they're traveling in the same phase. They're in phase and traveling to the right. When you combine these two waves, if there's no phase difference between them, you just get an amplitude which is twice as great. When phi is 0, this cosine 0 would be 1. You get 2a times that. Okay. When there's a phase difference, of 180 degrees, okay, so you have two speakers. When this guy is producing a crest and this guy is producing a trough, you send these two waves out, they'll exactly cancel each other.
You won't hear anything?
You won't hear anything. You guys see that? So how do I know you're not hearing anything? Okay, so let me do it. Okay. I sent these two guys, and when they got to you, they canceled exactly. How can you tell the difference between two waves are being sent or nothing is being sent at you? How do you tell the difference? All right, so the question is the following. I had two speakers, and Eli was sitting there. This wave reached with a crest. this wave reached with a trough, and they exactly canceled each other. So how does he know if sound is being played or two waves are canceling each other?
You can go to a slide series.
So you just move to a new location, okay? So you just move to new locations, okay? So when you have multiple waves and there's destructive interference and constructive interference, in other locations there'll be constructive interference. So energy is being redistributed, okay? So the only way you can tell if any sound is being played, you got to move around, okay? And I'll show you a little app for that in a little bit, okay? All right, so when the phase difference is pi, you have destructive interference. So in this case, the phase difference was n pi, and okay, and there was perfect cancellation, or n being odd, okay. There was perfect cancellation. That is destructive interference. And we use that phenomenon in many of your detectors, okay. So interference is used in many places. And so in general, when the phase shift is that, so here are two waves, sine waves combining that are traveling in the same direction with that phase difference. And there is the phase difference. Again, when phase difference is pi, cosine pi by 2 is 0, and the amplitude of that wave is 0, and you have complete destruction. All right, these were two waves traveling in the same direction. Now what we'll do is we'll make them travel in opposite directions. Okay, so what we'll do is, oops. Okay, so we'll come back to those slides. Let's make two waves traveling in opposite directions. So again, here's one wave traveling to the right, another wave traveling to the left. The amplitudes are the same, the wavelengths are the same, and the frequencies are the same. Why would we be interested in this? See, this is what happens when you play a guitar. So you pluck a string, the wave travels to the right. At the bridge, it gets reflected. So here's a wave traveling to the right, it gets reflected, and an identical wave is traveling to the left. Okay. That's what happens in all musical instruments. When you excite a musical instrument, you set up a wave that travels in one direction, it gets reflected at a boundary and travels back. Okay? So in musical instruments, you have two identical waves traveling in opposite direction. And let's see what happens. They combine, and at any given location, when you add these two guys up, there is the resultant. What is it that you notice? So for a wave to travel, you need x minus t. Okay, here the x and t got separated. So this is a static portion, and the t, all it's making you do is oscillate. So now this is not a traveling wave, this is a standing wave. Okay? And that's where the name comes from. So let me show you. So we're looking at superposition of two waves. Now we're going to superpose, in a given medium, we are going to superpose two identical waves traveling in opposite direction. Okay. So what this is showing you is this is a stationary wave and a traveling wave superposing, and then you get this is also traveling. Okay, so two sine waves traveling in opposite direction create a standing wave. So now we'll have two identical waves traveling in opposite direction, which is what we're looking at in the slides. and there they create a standing wave. Yeah. So that's what you're doing in musical instruments, exciting standing waves. All right, so when you pull a guitar string, you've excited a standing wave. Now, when a string vibrates, it makes sound, but you don't hear, I mean, it's hard to hear the sound because the intensity is not too large. A string cannot move too much air. So what do you need to hear the sound?
The hole in the middle,
I'm sorry? You need amplification.
chain guitar comes from the hole in the middle, right?
Right. That air, that's resonance. So, okay. So you need the acoustics box is amplifying the sound. Okay. Or you can use, we'll learn next semester how to amplify it electronically. That's an electric guitar. Okay. So musical instruments will have, all musical instruments will have something that vibrates. Okay, you're setting up standing waves, and then you have to have some kind of amplification device. All right, so that's standing waves. All right, so you saw that when two waves reach with the opposite phase, you have destructive interference when the phase difference, when two waves are traveling in the same direction and the phase difference is pi, then you have destructive interference. Okay, this is a phasor technique. You saw how to add two waves, but when you have multiple waves, so let's say multiple waves are reaching at a given location, A1 sine kx, and we are keeping this simple. We have the same frequency and wavelength. Okay, so here's a wave with amplitude A1. Frequency, wavelength and frequency are the same for all these waves. The amplitude is changing, the phase is changing. And adding these guys trigonometrically can be very challenging. Okay, and you encounter situations like this. So here's a technique for adding all those waves. So this is one wave, this is one wave, there's a second wave, and you can keep adding them. There's the resultant wave. Okay? So you see, this is like the y component of a vector. There's the amplitude of the vector. The sine function gives you the y component. Okay? So there's the phasor, the y component. You can see that as time increases, this angle decreases. So as time increases, this is rotating, this phase is rotating clockwise. Okay, so that's when you have to add multiple waves, you use this technique. Okay, so, and that's all I'll say about this. All right, till now what we've been doing is talking about a wave traveling in one medium. Okay, now let's say light is coming, it's traveling in air, and then it hits my glasses. Okay, now that's a different medium. Okay. So what happens, part of the light is reflected and most of the light goes through. Okay. So we want to know how light is reflected. Okay, so for instance, if light were traveling from glass and hit air, the reflection properties would be different than when it, so here's light traveling through air, it hits glass, and then when it travels through glass and then hits air, the reflection properties are different. Okay, so we'll talk about that. So reflection, fixed end. Okay, so we'll use a string as an example. Okay, so here's a pulse that's traveling. When the string end is fixed, a positive pulse upon reflection becomes negative. Okay. So let me show this to you. Okay, so here's a pulse that is traveling. Okay, so when a wave hits a hard boundary, a positive pulse becomes negative. When it hits a soft boundary, a positive pulse remains positive. All right, so this is when light travels from air to glass, it gets reflected like that. When light travels from glass to air, it reflects like that. Okay, and so this, you have to know this kind of stuff for thin film reflection. Okay, so for instance, anti-reflecting glasses, all it is they have a uniform coating, they have a clear coating of a certain thickness that is canceling so this is thin film optics. Here's glass, here's the thin plastic coat that they charge you a whole bunch of money for. Okay. This is a hard reflection. On a hard reflection, the reflected wave comes back like that. And this is a soft reflection, comes back like that. And so this wave and this wave cancel each other. So you don't see glare. Okay, so the light reflected off the glasses doesn't give you a great glare. Okay, so what that does is, so if you have glasses like this, and if you have an anti-reflective coating, then you can see my eyes properly. Okay? And if you don't have that coating, if you don't pay that whatever money, you won't see the eye of the person. Okay. All right. Okay, so here is a guitar string. You can excite it and it vibrates like that. So that is the lowest frequency in which it can vibrate. And these are all standing waves, okay? So the waves are not traveling. This is the next higher frequency you can also excite it at. This is the next higher frequency. Okay. These frequencies form a harmonic sequence. So if this frequency is 50 hertz, that's 100 hertz, that's 150 hertz, and so on. Integer multiples of the lowest frequency you can excite. Okay, they form a harmonic series. So the frequency at which this thing can vibrate, so the frequency at which this can vibrate is n is an integer, v is the velocity of the wave on the string divided by 2L. Okay? So n 2L square root of tension in the string divided by mu, the weight of the string, mass per unit length of the string. So what we are seeing here is this guitar string can only vibrate at certain frequencies. Again, n is integer. So how do you play music on a stringed instrument? How do you
You press down the string to shorten it.
You're changing the length of the string. Okay. So smaller the length of the string, higher the frequency, higher the pitch. And that's one thing you have under your control. What is the other thing that you can control?
Have different strings.
Yeah, you have different strings, 6 or whatever number of string. Heavier the string, lower the pitch. Okay, so that's how you produce music. Yeah, all right. So for a given length of string, the frequencies are integer multiples of the fundamental frequency. Okay, they form a harmonic series in a string. Look at this, a drum. Let's say that's the lowest frequency you can produce. The next higher frequency you can produce is not an integer multiple times that. It's 1.59 times that. The next higher frequency is 2.14 times the lowest frequency. So on a drum head, the frequencies do not form a harmonic series. Okay. So let me show you these drumhead vibrations. Yeah. All right. So here's a drum head. There is the fundamental mode. Yeah. That's the lowest frequency at which it's vibrating. There's the next higher mode. Okay. So when you're getting drum lessons, you're learning to hit the various spots on the drum head to excite various modes. Yep. All right, guys, so we will stop here.